This is a Sutotal production. Hello Chem Minions, this is Sutotal here, and this is going to act as our third practice video for chapter 5. So here we're looking at energy diagrams. So the first question here looks at two different energy diagrams, and we're kind of focusing on how many steps are in these. We need to identify each individual step, but also which is the rate determining step, and then important aspects of like where would we see our reactants and our products, our intermediates, how would we look at activation energy and transition states for these steps in the energy diagrams. So firstly, when we look at an energy diagram, you really, in order to determine how many steps there are, you just count the number of peaks. So if you notice, there's a peak here and there's a peak here. So there's actually two steps. We know that this corresponds to a two-step reaction. Okay. Now from there, the way it works, your steps go from kind of the low point on either side of the peak. So your first step here would start here, but it would end right in here, right? So from there to there, that is step 1. All right, and so then from here to here, right, this would encompass step 2. All right, now in determining the rate determining step, we need to kind of go ahead and identify everything first. So in reading from left to right, we're always looking at the leftmost side is the beginning of the reaction. And so what's in the beginning of a reaction? Reactants. So this area right here, right, this would be where we would find our reactants. And then the very end of however many steps there are, the very last part, this area right here would relate to the products. Okay. Now, from there, your intermediates are this area right here, right in kind of the middle of the steps, right? The end of the first step, the beginning of the second step. So this area right here, is where we would find our intermediate. Okay. And then from there, the transition states, I use this symbol like a little TT, a little cross. All right, these are your transition states. Okay. And then lastly, your activation energy. Every step has an activation energy to it. It's also called like an energy threshold or an activation barrier. And so what is that barrier? Well, for this first step, from the beginning of the step to the highest point of that step, this region right here, this would be the activation energy associated with the first step. So I would label this like EA1. All right. And then looking at our second step, the beginning of that step to the highest point, so this little bitty area right here, from here to here, this would coincide with our activation energy for step 2, or EA2. 2 steps, 2 activation energies. And so when we look at this, we have to say, well, which one of these includes a whole lot more energy? We would have to say step 1. The activation energy there is much larger than it is for the activation energy at step 2. So this tells us, since EA1 is much greater than EA2, that tells us that we can infer that step 1 is our slowest step, or our rate determining step. Okay, so step 1 is our rate determining step because of that activation energy. All right, now if we do the same thing for the second one here, hopefully you can tell, right? We've got a peak here, we've got a peak here, and we've got a peak here. So there are definitely 2 steps. And so where the kind of the edges of each step would be, this is the beginning of the step, and then this peak minimum right here, that would be the end of step 1. So all of this would be for step 1. So this would also be the beginning. This is the end of step 1, but also the beginning of step 2. And then this right here would be the end of it. So all from there to there would be step 2. All right, now as we go to label things, remember the very beginning is our reactants. So I'm going to just put an R there for reactants. The very end would be our products. So I'm going to put a P for products. And then the transition states, those are those two peaks. So we have 2 steps, 2 transition states. And then this area right here, right? So the end of step 1, but also the beginning of step 2, this is where you find your intermediate for this reaction, whatever it is. And then if we look, it wants, so we did the reactants, the products, intermediates, and the transition state. So now for activation energy, remember, right, there, for every step, there's an activation energy, right? And it's the beginning of the step to the highest point of that step. So that would be from here to here. So this would be EA1, activation energy 1. And then for this guy, it would go from here to here. So let's go over. So that would be the activation energy for step 2, EA2. And so based off that, can we determine the rate limiting step or the rate determining step? Yes, because EA2 is much larger than EA1. So because EA2 is much greater than EA1, that tells us that EA2 is slower, aka that means it is the rate limiting or rate determining, I misspelled it, but rate determining step. You'll have to excuse my inability to spell right now, but that's supposed to say rate determining step. All right, next up for number 7 here. So we have a reaction here, and we have 2 energy diagrams. And so based off this, it says for this reaction, which energy diagram do you expect it to coincide with? So what we can see is this is a 1-step reaction. Okay, so, and these are 1 step, right? There's only 1 peak in them, so they're 1 step as well. So we can't use the number of steps, right? Because we only see 1 arrow here, right? So we don't see the formation of intermediates for this. We're seeing 1 step take place. Now, what do we have to do? We actually have to look at the energy associated at the beginning and at the end. So here, if we were to compare this energy, we call this Gibbs free energy. So the delta G here is what? Did it gain or lose energy? It lost it. So here, it's some type of negative number, right? So if the delta G is negative, it lost energy. What does that mean? That means from reactant to product, the product should be more stable. Products more stable, right, than the reactants, okay? Now, if we look over here, we see the opposite, right? When we look at the delta G for the reaction here, and I guess I should put delta G reaction, right? Here, the products are higher energy than the reactants, so it's a plus. We don't know a number, but we know it's plus. So what does that mean? That means now the reactants are more stable. Reactants more stable than the products, okay? So that's what we have to look at. When we look at this reaction, what seems to be more stable? And when there's something with a charge, it's always easy to tell because you can compare the 2 charges, a negative oxygen versus a negative hydrogen. How do we compare those 2? We look at their electronegativity. Which one's more electronegative? If you look on the periodic table, right, you're going to see that oxygen is way over there on the right-hand side, right? That's where the more electronegative elements tend to be. So if oxygen is more electronegative than hydrogen, which one's more stable when it has a negative charge? That guy, the negative oxygen. It's more stable to have a negative oxygen than a negative hydrogen. So I'm going to put a cross there, an X on it. All right. So that means our more stable situation is on our reactant side. So based off this, we just said, right, products more stable, reactants more stable. So I would believe that this reaction coincides with energy diagram B. That's my best guess. All right. Next up, here we have, it looks like there are a bunch of things going on here, but you notice all of this happens in 1 step. This right here is showing me a 1-step reaction. So I can easily just infer that's a 1-step, and this is a 2-step reaction. Right? We already did that practice previously. So that's a 1-step reaction, so that coincides with A. All right? It's going to be very difficult for you to look at stability here, but you do have something negative and now everything's neutral, so that is kind of favorable. So having more stable products as you do here is also favorable, but you see the same thing happening here, right? The reactants are less stable, the products are more stable in both of these, so that's kind of hard for you to tell. So you really just have to look at the number of steps. All right, so hopefully looking at all this energy diagram information, this kind of helps you in the future. So as always, adios and stay weird. SuTotal is out.